In this grand finale, we will see what happens to the motion of our spring when there is resonance. And as you'll see, all hell will break loose. So let's consider y double prime plus 4y, this time 12 cosine of 2t with initial position 1 and initial velocity 6. So as usual, I just want to outline everything. So we have the homogeneous solution, or what's called the steady state solution. So the auxiliary equation here is r squared plus 4 equals 0. So r is plus minus 2i. And then and therefore, not quite done. Our homogeneous solution, or what's called the steady state solution, is a cosine of 2t plus b sine of 2t. And now for the particular solution, let's look at the right-hand side. Particular solution. So here the right-hand side, which is 12 cosine of 2t, well, this time it corresponds to the root r equals plus or minus 2i, which coincides. So because the roots coincide, that's when we have resonance. So the roots coincide. Side. Therefore resonance. And therefore, remember, add this extra t. So usually we would have yp is a cosine of 2t plus sine of 2t. But now we have to add an extra t. And again, it makes sense because if you had a cosine plus b sine, it would be the same as the homogeneous solution. So if you plug it in, the right-hand side would be 0 and not 12 cosine 2. All right, very good. And then, as I said, you can see the details in the notes. If you plug in yp double prime plus 4yp equals 12 cosine of 2t, then it turns out you get a equals 0 and b is 3, which now gives you the solution. So the transient solution here is 3t sine of 2t. And then the general solution, so y equals y0 plus yp, would be a cosine of 2t plus b sine of 2t plus 3t sine of 2t. And then, last but not least, you plug in the initial conditions. So y of 0 equals 1. And y prime of 0 is 6. And what you end up getting is a equals 1 and b equals 3. And therefore, our answer, in this case, y of t is cosine of 2t plus 3 sine of 2t plus 3t sine of 2. And once again, like that movie, let's analyze this. So the question is, does this forcing term in this case have an effect? Well, if you look at the solution, it starts out, I believe, at 1. But then It just oscillates, oscillates. Oh my God, it becomes so big. You cannot control it anymore. Mayday, mayday. I guess June day, June day. So in fact, you might say there is a pretty big effect of the force. So if there is resonance, which is in this case, so here, there is resonance, which kind of causes a solution to blow up. Solution to blow up. Oh. And that is because, let me erase this here, because of this 3t sine of 2t term. T goes to infinity, so 3t sine of 2t like goes to plus minus infinity in some sense. So what's the moral? In this case, the forcing term has a big effect. F of t, which I think was a 12 cosine of 2t, has a big effect. Big effect. And this is extremely important in applications. I do want to tell you two really cool applications. One is, you may have seen this before, if you swing on a swing and you move your feet at the exact same frequency as the swing, suddenly the swing becomes very big. You go forward and backward very quickly. And that's because of resonance. Sometimes it has no effect if there's no resonance, but if you really move your feet at the right time, then you do have this resonance effect. The other one, a bit more morbid, but resonance literally caused the Tacoma Bridge to collapse in 1940, because what happened, I believe, was there were some soldiers walking on that bridge, and the soldiers walked at the exact same frequency of the bridge that caused it to collapse. In fact, I want to show you a cool YouTube video on this. I know, so meta, YouTube within YouTube, where you can really see the Tacoma Bridge wiggling very wildly. See? And again, this is because of resonance. Luckily, though, no one got hurt. I heard there was a dog on the bridge, but they were doing okay too. But again, this is extremely important, I would say, in physics and engineering. Beware of the resonance term. So that little t that you learn in this course actually has a very big effect.